Imagine a world where electricity does not power cities, does not light homes, does not move trains, does not carry voices across oceans. A world where night truly means darkness, and where the forces that run modern civilization remain completely unknown. For most of human history, that was reality. Electricity was not understood, not controlled, and not even properly defined. Its discovery was not a single moment, nor the work of one individual, but a gradual unfolding that stretched across centuries. The earliest recorded observation of electric behavior dates back to around 600 BC, when Thales of Miletus described a curious effect involving amber. When rubbed with fur, amber attracted light objects such as straw and feathers. To the ancient Greeks, this phenomenon seemed almost alive. The Greek word for amber was electron. And although Thales had no knowledge of electrons or electric charge, his observation represents the first documented account of static electricity. For many centuries after Thales, little progress was made in understanding this strange force. The effect remained a curiosity rather than a subject of systematic investigation. It was not until the late 16th century, during the scientific revolution, that electricity began to be studied with careful experimentation. One of the first major contributors to this shift was the English physician and natural philosopher William Gilbert. Born in 1544, Gilbert is often regarded as one of the founders of electrical science. Although best known for his studies of magnetism, he carefully investigated the properties of amber and other materials that exhibited similar attractive effects when rubbed. Gilbert observed that not only amber, but also glass, sulfur, and various crystals could attract small objects after friction. Recognizing that this behavior was distinct from magnetism, he introduced a new term, derived from the Greek word philamba. He referred to such materials as electrics and described the force they produced as electric. In doing so, he laid the linguistic and conceptual foundation for modern electrical terminology. Gilbert also constructed a device known as a versorium, a lightweight pivoting needle capable of detecting electric attraction. This instrument allowed him to observe electric effects more systematically. He further noted that moisture, such as a thin layer of water, disrupted electric phenomena, while oil did not. Though he lacked a modern framework, these observations hinted at the difference between conductive and insulating materials. The next significant advance came in the mid-17th century with the work of the German scientist Otto von Guericke. Around 1650, von Guericke constructed one of the earliest electrostatic generators. He cast a sphere of sulfur, mounted it on an axle, and rotated it while pressing his hand against its surface. The friction generated static charge, producing visible sparks in a darkened room. For the first time, electricity was not merely an invisible force of attraction, it could produce light. This demonstration transformed electricity from a subtle curiosity into a dramatic physical phenomenon. Several decades later, in 1709, the English experimenter Francis Hauksbee refined von Guericke's design. Hauksbee used a hollow glass globe from which air had been evacuated. When rotated and rubbed, the globe emitted a glowing light inside. The illumination was reportedly bright enough to read by. These experiments further demonstrated the luminous effects of electricity and increased scientific interest across Europe. Despite these striking displays, electricity was still largely confined to short-lived static effects. The question remained whether electric charge could be transferred over distance. In 1729, the English scientist Stephen Gray made a breakthrough discovery. While experimenting with a glass tube sealed with corks, Gray noticed that after rubbing the tube, the corks themselves attracted small objects. This indicated that electric charge had traveled from the glass to the cork. Gray began testing a wide variety of materials. He discovered that some substances, such as metals and moist threads, allowed electric charge to pass through them, while others did not. In one series of experiments, he successfully transmitted electricity across nearly 900 feet using suspended lines. During these experiments, Gray observed that when conducting lines were supported by silk threads, electricity traveled successfully when supported by metal wires. The charge dissipated. This distinction revealed a fundamental principle. Certain materials conduct electricity while others insulate against it. Gray's work marked the transition from simple electrostatic demonstrations to the controlled transmission of electric charge. Shortly thereafter, the French scientist Charles-François de Sistine-Dufay expanded the understanding of electric behavior through systematic experimentation. He discovered that electric charge existed in two distinct forms: Objects charged in one way repelled similarly charged objects but attracted those charged differently. Dufay referred to these as vitreous and resinous electricity. Though the terminology would later change, his recognition of two types of charge laid the groundwork for the modern concept of positive and negative electricity. The study of electricity gained further prominence in the mid-18th century, particularly through the work of the American polymath Benjamin Franklin. Franklin proposed that electricity was a single fluid rather than two separate substances. He introduced the terms positive and negative to describe electrical states, terminology that remains in use today. In 1752, Franklin conducted his most famous experiment to test the hypothesis that lightning was a form of electricity. During a thunderstorm, he flew a kite equipped with a metal key attached to its wet string. As electrical charge accumulated from the storm clouds, sparks were observed at the key. This experiment demonstrated that lightning and laboratory-generated electricity were manifestations of the same force. Franklin's work not only unified terrestrial and atmospheric electricity, but also led to the invention of the lightning rod, providing practical protection against lightning strikes. As understanding of electric charge advanced, scientists sought methods to store it. In 1745, the German cleric Ewald Georg von Kleist developed a device capable of holding electric charge. Shortly thereafter, the Dutch scientist Pieter van Musschenbroek independently created a similar apparatus at the University of Leiden. The device became known as the Leyden jar. The Leyden jar consisted of a glass container lined with conductive material and fitted with a metal rod. It functioned as the first capacitor, allowing electric charge to be stored and later discharged. This innovation represented a crucial step toward controlled experimentation and practical application. By the late 18th century, the focus shifted from static electricity to continuous current. In the 1780s, the Italian physician Luigi Galvani observed that frog legs twitched when touched by metal instruments during electrical experiments. Galvani concluded that animals possessed an intrinsic form of electricity, which he termed animal electricity. However, his contemporary Alessandro Volta disagreed with this interpretation. Volta argued that the observed effects resulted from the contact between different metals, rather than from the frog tissue itself. To test his theory, he constructed a device composed of alternating discs of zinc and copper, separated by cloth soaked in salt water. In 1800, Volta introduced the voltaic pile, the first true battery capable of producing continuous electric current. Unlike static machines, which generated brief discharges, the voltaic pile provided a steady flow of electricity. This invention marked a turning point, transforming electricity from an intermittent phenomenon into a sustained source of power. The early 19th century brought further discoveries linking electricity and magnetism. In 1820, the Danish scientist Hans Christian Ørsted observed that an electric current passing through a wire deflected a nearby compass needle. This demonstrated a direct relationship between electric currents and magnetic fields. Building upon this insight, the English scientist Michael Faraday conducted a series of experiments that would fundamentally change the world. In 1831, Faraday discovered electromagnetic induction. He found that when a magnetic field around a conductor changes, an electric current is induced within it. Faraday demonstrated this principle using coils of wire wrapped around an iron ring. When current in one coil was switched on or off, a brief current appeared in the second coil. He later constructed a device in which a copper disc rotated between the poles of a magnet, generating continuous direct current. This apparatus is regarded as the first electric generator. Faraday's work established the principle that mechanical motion could produce electricity. This concept underlies modern power generation, from steam turbines to hydroelectric dams and wind turbines. Subsequent scientists expanded the theoretical framework. James Clerk Maxwell formulated equations unifying electricity and magnetism into a single electromagnetic theory. His work provided the mathematical foundation for understanding electromagnetic waves, including light itself. In the late 19th century, innovators such as Nikola Tesla and Thomas Edison developed systems for large-scale electric power distribution. Their efforts led to the electrification of cities and the widespread adoption of electric lighting and appliances. Between the late 16th century and the early 19th century, electricity evolved from a poorly understood attraction between rubbed materials into a controlled and measurable force capable of powering societies. This transformation required the contributions of numerous scientists, each building upon the work of those who came before. The discovery of electricity was not a single event. It was a gradual progression, moving from observation to experimentation, from terminology to theory, and from sparks in darkened rooms to generators, capable of sustaining modern civilization. Today, electricity operates quietly behind walls and beneath streets. It powers communication, transportation, medicine, and industry. Yet its origins trace back to a simple observation made over 2 millennia ago, when a philosopher noticed that amber, when rubbed, could attract straw. From that modest beginning emerged one of the most transformative discoveries in human history.